Welcome to the deep dive. You're likely hearing about artificial intelligence everywhere. And today we're cutting through the noise.
Yeah, there's a lot out there.
Right. We want to give you the essential understanding of what AI is right now. Think of this as your quick flight up to 30,000 feet for a clear view of the AI landscape.
Exactly. Our goal in this deep dive is really to provide you with that high-level understanding, from the foundational ideas that make it all work.
The real basics.
The basics, yeah. All the way to current technologies like large language models, Llama is a good example, and even a glimpse at the hardware that powers these systems.
And we looked at quite a few sources for this.
We did. Articles explaining machine learning models, the crucial bit about data preparation, how large language models and transformers work, and even some practical takes on fine-tuning.
Okay, let's take off then. Basics first. What exactly is machine learning in simple terms?
Okay, so in essence, machine learning lets computers learn from data. It gives them the ability to spot patterns, make predictions.
Without us programming every single step.
Precisely. Instead of writing tons of if this then that code, we feed algorithms data and they figure out the patterns themselves.
Ah, okay. And you mentioned algorithms and models. Are they the same thing?
Good question. No, not quite. The algorithm is like the recipe, the set of rules or instructions.
It's a method.
Right, the method. The model is what you get after you apply that algorithm to your data. It's the learned result, the thing that actually captured those patterns.
Got it. Algorithm is the tool. Model is the finished product from using that tool on data. So how does this learning actually happen? What's the process?
We usually call it training. Basically, you feed data into the model, and it adjusts its internal settings. We call them parameters.
Like little dials inside?
Sort of, yeah.
Right.
It tunes those dials to minimize mistakes in its predictions. It learns to connect inputs with the outputs you want, like predicting ice cream sales based on temperature.
Okay, makes sense. Higher temps, probably more sales.
Yeah.
The model learns that connection. Now, I know there are different ways machines learn. Different styles.
That's right. There are four main approaches. First up is supervised learning.
Supervised. Like a teacher.
Kind of. The model learns from labeled data, so we give it examples where we already know the right answer, the input, and the correct output.
Like the ice cream example. Temperature input, actual sales output.
Perfect example. Linear regression is a classic technique there, as our sources mentioned. You show the model the answers, so it learns the relationship.
So it learns by example. What if you don't have all the answers labeled?
Then you might use unsupervised learning. Here, the model gets unlabeled data and has to find patterns on its own.
Like sorting things.
Yeah, clustering is a common use, grouping similar data points together without being told what the group should be beforehand.
Interesting. And you said 4 types.
Right. Third is semi-supervised learning. It's a mix, uses some labeled data and a lot of unlabeled data. Pretty useful when labeling everything is just too expensive or time-consuming.
Okay, makes sense. Best of both worlds sometimes. What's the last one? Sounds like training a dog.
Haha. Yeah, that's reinforcement learning. The model learns by trial and error. It gets feedback rewards for good actions, penalties for bad ones.
Like finding its way through a maze.
Exactly. Gets a reward for moving closer to the exit, a penalty for hitting a wall. Over time, it learns the best path to maximize those rewards.
Fascinating. Okay, so supervised, unsupervised, semi-supervised reinforcement. Where does deep learning fit in? We hear that term constantly.
Right. Deep learning is really a powerful subset of machine learning. It often uses these complex models called neural networks with many, many layers, hence deep.
More layers, deeper learning.
Basically, yeah. These deep models can automatically learn very intricate patterns, especially from huge amounts of data. They often figure things out that older machine learning methods might miss. They evaluate algorithms and improve themselves.
Okay, so ML is the big field. Deep learning is a very powerful technique within it. Got it. Now, none of this works without the right fuel, does it? Data.
Absolutely critical. Data is the lifeblood. You can have the smartest algorithm, but with bad data. Garbage in, garbage out, right?
Totally. So data preparation must be huge.
It's vital. Our sources break it down into about 4 main stages.
Okay, walk us through them. Step 1.
Data collection. First, you figure out where your data comes from. Primary sources you gather yourself, or secondary sources someone else collected.
Makes sense.
Then you actually acquire it, maybe label it if you need supervised learning. There's also something called data augmentation.
Augmentation. Making more data.
Yeah, especially in deep learning, you kind of creatively modify your existing data to make more training examples. Clever trick. Then you integrate data if it's from different places, maybe aggregate it, combine data points.
And you need to understand the data you're collecting too, right?
Definitely. That's exploratory data analysis, or EDA. It's like getting to know your data, its quirks, its characteristics. You need to make sure you're collecting the right stuff for the AI to learn properly. One source put it nicely. Collection of the right data set ascertains the right data output.
Good ingredients make a good cake. Okay, so you've collected the raw data. What's next?
Data cleaning. Dealing with the messy bits.
The not so glamorous part.
Maybe, but essential. Handling missing values, lots of ways to do that in code like Python or R. Removing noisy data stuff that's irrelevant, wrong, or duplicated. Techniques like dbScan can help smooth things out and find outliers.
Okay, clean data is happy data. Then what?
Data transformation. This is about getting the clean data into the right shape for your model.
Reshaping it.
Yeah, changing its format, structure, maybe the values, like breaking down months into weeks, that's attribute decomposition. Or discretization, creating categories or bins and putting data points into them.
So making it digestible for the algorithm. And the last step.
Data reduction. Look, we have massive data sets now, right? Storing and analyzing all that costs a fortune.
Big data, big bills.
Exactly. So data reduction techniques compress the data, make it smaller, but keep the important information. Things like data cube aggregation can help summarize multi-dimensional data. It saves money, speeds up processing.
Collect, clean, transform, reduce.
Got it.
Okay, data's ready. Let's talk about the really hot stuff now. Large language models and transformers. What's the deal?
Okay, large language models, LLMs. They're a type of neural network, but huge, billions, sometimes trillions of those parameters we talked about.
Trillions, wow.
Yeah, they're trained on just massive amounts of text, usually using self-supervised or semi-supervised learning. And the key architecture behind many of them is the transformer.
The transformer. Sounds cool. What does it do?
It's a specific neural network design, really good for sequential data like language. Its big innovation is how it handles relationships between words, even if they're far apart in a sentence.
How does it do that?
It converts text into numbers, but then it uses this clever thing called an attention mechanism. It basically weighs the importance of different words when it's trying to understand or generate text.
So it pays more attention to key words.
Yeah.
Like we do in reading.
That's a great analogy, exactly. It figures out which words are most relevant to the context instead of just processing them one by one mechanically.
That makes sense. And how do these LLMs get so smart? You mentioned training.
Right. It's usually a two-step process. First, pre-training.
Pre-training.
Yeah. You train the model on a huge general text data set. Think like the whole internet, books, articles. It learns grammar, facts, common sense, how language works.
Building a general knowledge base.
Exactly. Then comes fine-tuning. You take that pre-trained model and train it more, but on a smaller, specific data set for the task you actually want it to do.
Like specializing.
Precisely. You adjust its parameters, check its performance, tweak things called hyperparameters, other settings, to optimize it for that specific job.
Pre-trained for breadth, fine-tuned for depth. Okay, now the sources mention names like BERT, GPT. How do they relate?
Yeah, those are famous transformer-based models. BERT, that stands for bidirectional encoder representations from transformers, is really good at understanding context. It looks at words before and after a target word. Great for tasks like understanding text or question answering.
Understand it, okay. And GPT?
GPT, generative pre-trained transformer, is more focused on generating text. It predicts the next word in a sequence. That's why it's good for writing, chatbots, that kind of thing.
Generation versus understanding.
Largely, yes. Then you have others like T5, which frames everything as text-to-text, tasks, translation, summarization, all in one model. There's even VIT, the vision transformer, which adapts this for images. And Roberta, which is like an improved version of BERT with better training technique.
It's amazing how flexible that transformer design is. Okay, another term floating around is context window. Why is that important for LLM?
The context window is basically how much text the LLM can look at or remember at one time when processing input.
It's short-term memory.
Kind of, yeah. It's crucial. It affects how well the model understands complex instructions, keeps track of a long conversation coherence, and gives relevant answers. A bigger window means it can handle more information.
How big are we talking?
Well, for example, GPT 3.5 or Llama 2 might have a 4K token window that's roughly maybe 6 pages of text, but newer models have much larger ones, like 32K tokens, which is closer to 50 pages.
50 pages. So bigger is always better. More memory, better understanding.
Generally, yes, it helps with longer tasks, but There's this interesting thing called the missing middle problem.
Missing middle.
Yeah, sometimes with really large context windows, models seem to struggle to recall or use information that's stuck right in the middle of a long piece of text. They might remember the beginning and end better.
That's counterintuitive. You'd think more space means easier access.
You would, but maybe the way attention works makes it harder to pinpoint things in the middle of a huge sea of text. Researchers are working on it, though. With techniques for context length extrapolation, things like rotary position embeddings and an extension called yarn, they try to stretch the effective context window beyond what the model was originally trained for.
Stretching the memory?
Sort of. And yarn is interesting because it tries to do this without hurting performance on shorter tasks, while enabling these really long contexts, maybe even up to 128,000 tokens.
Whoa. But processing that much must take serious horsepower.
Oh, absolutely. Trying to run models with massive context windows on your phone or a standard laptop, that's a huge challenge. Not enough processing power, not enough memory.
Right. Okay, let's ground this a bit. Llama was mentioned. What is Llama in this picture?
Llama is a specific, well-known large language model. Its autoregressive predicts the next word, like GPT.
So it generates text.
Yes. It was trained on huge amounts of unlabeled text. It's considered a base or foundation model.
Meaning you can build on it.
Exactly. You can fine-tune it for specific things, and it has a context window too. Llama 2 started with 4K tokens, for instance. There's also the Open Llama project, which made a version publicly available, which was a big deal for research.
So Llama is one specific brand or type of these transformer-based LLMs.
Gotcha.
Let's talk hardware now. GPUs always come up with AI. Why GPUs, not just regular CPUs?
Well, training these big transformer models is just massively computationally expensive, really time-consuming.
Wow, expensive.
The sources say it can take thousands of powerful GPUs running nonstop for weeks to train a big model from scratch.
Thousands for weeks. Wow.
Yeah. Now, you can fine-tune smaller models on less intense hardware. Someone mentioned trying CLORF fine-tuning on a single high-end gaming GPU.
Possible, but maybe not practical for big jobs.
Right. For serious training or significant fine-tuning, you typically need cloud GPUs or dedicated hardware clusters. The sources don't go deep into CPU versus GPU architecture differences, but the key is parallel processing.
Parallel, doing lots of things at once.
Exactly. GPUs are designed to handle many calculations simultaneously, which is perfect for the math involved in neural networks. CPUs are generally faster for tasks one after another, sequentially. For AI training, parallel is way faster.
Okay, so GPUs are the workhorses because they can multitask on a massive scale. That makes sense. So training is this huge effort. Why bother fine-tuning then, if it's already trained on so much data?
Because pre-training gives general knowledge, but fine-tuning gives specific expertise. It's about adapting that powerful foundation model for your particular use case.
Taking the generalist and making it a specialist.
Perfect analogy. You train it further on a smaller, task-specific data set. Think of the pre-trained model as having a broad education.
Like a liberal arts degree.
Yeah. And fine-tuning is like sending it to med school or law school. It leverages all that broad knowledge, but hones it for specific skills.
And is more efficient than starting from scratch every time.
Much more efficient. Building these models from zero is incredibly resource-intensive. Fine-tuning lets you inherit the stability and power of the pre-trained model.
Give us some examples of fine-tuning in action.
Okay. Take a general LLM, fine-tune it on programming code and documentation, and it gets much better at writing or understanding code.
Makes sense.
Or an image model trained on general objects, fine-tune it on pictures of birds, and it becomes a bird species identifier. Or fine-tune an LLM on, say, Shakespeare's plays, and it might learn to write in that style.
Learning a specific style. Cool.
Yeah. And for chatbots, there's instruction tuning, a type of supervised fine-tuning using prompt response pairs to teach the model to follow instructions better.
Teaching it to be helpful.
Right. And for even fuzzier things like helpfulness or harmlessness, there's RLHF reinforcement, learning from human feedback.
Okay. And didn't you mention ways to make fine-tuning less computationally heavy?
Yes. PEFT methods, parameter-efficient fine-tuning, things like LoRa and QLoRa, they cleverly update only a small subset of the model's parameters.
Why do that?
It drastically reduces the computing power needed, and it also helps prevent catastrophic forgetting, where the model forgets its general knowledge while learning the new specific task.
Keeps the general knowledge while adding the specialty. Smart. So where are we seeing these fine-tuned models being used in the real world?
Well, a big area mentioned in the sources, especially from user discussions, is chatbots. Companies fine-tuning LLMs on their own data.
Like customer service chats or internal documents?
Exactly. To create specialized bots for customer support or internal knowledge bases, they can answer questions based on that specific company data much better than a generic model.
That sounds incredibly useful. Any challenges there?
The user source mentioned that getting the data formatted correctly, often using specific tags like hashtag instruction, hashtag input, hashtag output, is really crucial, but can be tricky.
Formatting is key.
Definitely. And there's the choice between using hosted APIs, maybe like Azure OpenAI for better privacy, versus running models locally, offline, which gives more control but costs more upfront.
Trade-offs, as always. Is fine-tuning the only way to use these models with specific documents?
No, another popular approach is using vector databases and embeddings. Instead of retraining the model, you embed your documents, and the LLM can quickly search and retrieve relevant snippets to answer questions based on that document base.
Retrieval Augmented Generation, RAG.
That's the one. It's often faster and cheaper than fine-tuning for knowledge retrieval tasks. Also, it's worth remembering that base LLMs can inherit biases from their training data. Fine-tuning can be a way to try and mitigate those biases for specific uses.
An important point.
Yeah.
And these models don't just stay static, right?
No, the world changes, data changes. There's this idea of concept drift. Models need maintenance, maybe periodic retraining or fine-tuning to stay accurate over time.
Continuous learning.
And finally, we're seeing models being offered as APIs, basically, letting other businesses plug into these AI capabilities to solve specific problems, which also helps the developers recoup those massive training costs.
This has been incredibly insightful, a real tour from the ground up to the cutting edge. Let's try and sum up the key takeaways.
Sure, I think the big things are AI learns from data using algorithms. Machine learning is the core. Deep learning is a powerful part of it.
Right. And LLMs?
LLMs, built on that amazing transformer architecture, are incredibly powerful for language tasks, but they gain their general smarts through pre-training.
And then get specialized through fine-tuning, which makes them useful for countless specific applications. We also saw data prep is vital, GPUs are essential hardware, and Llama is a key example model.
Couldn't have said it better myself.
So wrapping up, considering how fast these AI models are evolving and how the tools to use them are becoming more available, it really makes you think, doesn't it? What new applications, what solutions might you out there listening imagine or even start exploring? The possibilities feel kind of limitless right now. Your understanding of these basics is really the launchpad. Thanks for joining us on this deep dive.